Chris. This one's going to be an interesting lecture, very upcoming field of research. And I plan to go over the following topics. So before talking about, what exactly is active interrogation, I want to provide a motivation on why there is a need for active interrogation, why the current existing techniques are not enough, and we have to go beyond the passive methods. And then we'll get into details on some of the ionizing radiations that are commonly used in active interrogation, and two important reactions that play a very that play a key role in active interrogation. That is neutron-induced fission, photon-induced fission, and finally, I'll talk a little bit about concept of active background. I'll be taking pauses, periodically throughout my presentation to see if there are any questions from the audience. You're welcome to post all of your questions in the chat, and also feel free to unmute yourself and just say out your question loud. That's totally okay with me. Alrighty, so let's get started. And the first question is, why active interrogation? Now, the answer to this question is to trying to solve biggest non-proliferation problem globally, and that is detecting hidden special nuclear materials. All the techniques that are currently being used for S&M detection, they are passive non-destructive assay techniques. But these passive techniques have certain limitations and challenges, and this is because of the nature through which passive techniques work. Now, passive techniques rely on the spontaneous radiation that is emitted from nuclear materials. So when we are relying on spontaneous emissions, there are two particles that are typical interest. One is the characteristic gamma rays that are emitted as a result of alpha or beta particle decay. And second, neutrons that are emitted as a result of spontaneous fission or alpha end reaction on low-Z materials. Now, let's take an example. Let's consider a special nuclear material, uranium-235. Now, uranium-235, the characteristic X-ray, out of all the X-rays that are emitted from U-235 are low energy X-rays. When I mean, low energy gamma rays. When I mean low energy gamma rays, we're talking less than 1 MeV in energies. Now, if we want to detect these low energy gamma rays, we need to have a detector that has excellent energy resolution at such low energies. And also, these low energies should be able to survive the shielding that may be present around the S&M and reach our detector so that we can get a signal. Again, the second signal, which is neutrons, uranium-235 has a very low spontaneous fission rate. So there are not neutrons emitted from the isotope, and therefore we cannot get, again, a detectable signal. So both characteristic gamma rays and neutrons are emitted in very small intensities, and therefore this poses a great challenge in passive NDA techniques. If you have shielding around the S&M, that will further complicate the detection of S&M. So in order to overcome these limitations, we use active interrogation. Professor Jovanovic, in his textbook, described active interrogation as the intentional bombardment of an object using ionizing radiation in order to induce nuclear reactions. Now, this nuclear reactions is very important in active interrogation because the type of nuclear reaction that happens in the target material help us detect these nuclear materials. We get very high energy particle emissions, and plus they are emitted at high intensity. So we have good signal strength, we have good source strength, and therefore we can detect these particles with our detection system. So the idea of active interrogation is to amplify the detectable signals to such an extent that we can easily detect them with our detection system. So what are the strengths of active NDA? Now, since we are using an ionizing radiation to interrogate the target material, this ionizing radiation can penetrate shielding materials. That is very, very important if we are trying to detect hidden special nuclear materials. And then when SNMs are bombarded with neutrons or high energy photons, fission reaction happens. And this is a very, very interesting reaction because when fission happens, within picoseconds, we get 2 to 3 prompt neutrons and approximately 8 prompt gamma rays. Not only prompt, but for up to several minutes after the fission reaction, we still continue to get delayed neutrons and delayed gamma rays. Now, both prompt and delayed signatures constitute the desired signal during our active interrogation. So to visualize what an active interrogation system looks like, so the yellow box can be sort of, thought of, a cargo container. Say it's being, there's a cargo container that has to be investigated to look for any possible hidden SNM. And then we have an interrogating source. This could be anything, neutron or high energy photons. We bombard this ionizing radiation, our interrogating source, onto the yellow box. And if there is an SNM present, then fission reaction will happen. And when fission happens, there will be neutrons, prompt gamma rays, and then delayed neutrons and delayed gamma rays will be emitted. And with our detectors, we will detect all these 4 important signatures. And then with proper analysis technique, we can identify the special nuclear material. So this is the motivation of why active interrogation is sort of gaining so much importance over passive techniques. And what exactly are we trying to achieve with active interrogation? The underlying idea is to amplify the signals from SNM so that they can be easily detected. So I'm going to take a pause here and see if anyone has any questions before I move on to the next topic. Okay, seems like there are no questions. All right, so I'm going to get into the next topic, and that is sources of ionizing radiation. So again, we can have 2 broad categories of ionizing radiation. The first one are your neutron sources. Commonly used neutron sources during active interrogation, californium-252, This one is a spontaneous fission source. So we get neutrons with energies over a very wide range, from thermal all the way up to 10 MeV or even higher. Then we have AMLI, AMB, and PUBI. These are all alpha N type neutron sources. AMLI is an epithermal neutron source. PUBI is a strong PUBI is a source that has neutrons with energies emitted at higher energy values. So by higher, I mean we're talking more greater than 2 to 3 MeV. So the spectrum is much more harder compared to the Watt spectrum that we are used to seeing from californium source. And then we have fusion sources from DD and DT generators. The advantage of DD and DT generators is that we get monoenergetic neutron source. So DD gives us about 2 MeV neutron source, and DT gives us 14 MeV neutron source. All these neutron sources have the ability to penetrate high Z shielding materials. So that's a very a big advantage of using neutron source in the active interrogation. And normally, we would want to detect prompt gamma rays and delayed gamma rays when we have neutron active interrogation scenario. It's not that neutrons cannot be detected. They can be detected, but they are a little tricky. Now, for instance, let's take an example of a DD generator being used in our active interrogation scenario. So DD emits 2 MeV neutrons. And then when fission happens, we also have prompt neutrons that are emitted up with the Watt energy spectrum. So if we want to detect neutrons from the fission events coming from SNM, we may use an energy threshold. So if we get a neutron greater than 2 MeV, then we know that this neutron is coming from the target material and not from the source material. So this is one way of detecting neutrons. Now with the DT generator, it's tricky because you have 14 MeV from you have 14 MeV source neutron. So we cannot simply put a threshold at 14 MeV. Because if we put a threshold at 14 MeV, then all the neutrons that are emitted from the fission event will not be detected. If you remember the Watt spectrum, majority of the neutrons are emitted with energies less than 1 MeV. So we're throwing away all the desired signal. So there is research ongoing to detect prompt neutrons, and detecting prompt neutrons is always challenging and tricky. Now, one thing I want the next type of ionizing radiation are photon sources. Photon sources, we have linear accelerators, isotopic sources, and laser sources. Now, photon source, obviously we know high Z shielding targets will attenuate the photon source, so they can only penetrate low Z targets. Since we are to make our detection system easier, we detect prompt neutrons and delayed neutrons during photon active interrogation. And in this case, detection of gamma rays is tricky due to the presence of the photon interrogating source. Now, how can we detect? Now, we can still detect gamma rays during photon active interrogation. And an example that I can give is we can use a pulsed photon source. So for example, linear accelerators, they are operated in pulsed mode. So we can detect gamma signatures in between the accelerator pulse, because in between the accelerator pulse, radiation will only come from the target material, and this radiation would be delayed gamma rays, and all of our source radiation is zero because there is nothing emitted in between the accelerator pulse. The same thing can be applied for neutron source. So DT, DD, and DT generators are operated in pulsed mode, so we can detect neutrons in between the DD and DT generators. And this way we can use engineering to detect signals in between the pulses. I see there was a question in the chat. That's a very good question. So the question is there any criticality risk with the active interrogation? So I am gonna answer that question in some time. We are getting to some of those concerns and challenges in active interrogation. But thank you for that question. Okay. All righty. So the next topic that I have is we want to talk about. So we have all these interrogating source, and first we will talk about neutron-induced fission reactions. We all are very familiar with neutron-induced fission reactions. The electricity that we get from nuclear reactors is based on this reaction, neutron-induced fission reaction. And to provide some idea on the numbers, we have, when neutron-induced fission reaction happens, the average number of prompt neutrons that are emitted per fission event is higher than what is normally emitted as a result of spontaneous fission. So for example, plutonium-239, spontaneous fission nu bar is about 2.6. But when we induced fission using thermal neutrons, nu bar is 2.88. And it further increases if we use neutrons with higher energy. So it goes to about 3.16 when fission is induced using 2 MeV neutrons. And prompt gamma rays, again, for an uranium-235 isotope, we get about 6.6 prompt gamma rays per fission. And these gamma rays are emitted with an average energy of slightly less than 1 MeV. Now, there are, as I mentioned earlier, we also have delayed signatures that are emitted. And these delayed signatures, the yield at which they are emitted is very small compared to the prompt neutrons. But they still give us some information on the material that's being investigated, because delayed neutrons will come from fission reaction, and we won't get delayed neutrons from any other reactions like photonuclear, where a neutron is emitted, photonuclear like gamma end reaction. So delayed neutron is again a very distinct type of particle that we get from the fission. And the same applies for delayed gamma rays. And again, all these gamma rays are emitted, they're low energy gamma rays. So we need to have high energy resolution detectors to be able to detect these gamma rays. I'm going to come to that question, which says about criticality risk with active interrogation. If S&M is being, so criticality is basically a function of two important things. One is the geometry, and then also the amount of the S&M that's actually present. Now, normally, when we are doing active interrogation, our idea behind active interrogation is to detect small quantities of hidden S&M. Because if the S&M is present in significant quantities, then passive detection systems will be able to detect that particular S&M. So the idea of active interrogation is to detect smaller quantities, and therefore the criticality is not a very big concern when it comes to active interrogation. The next type of reaction that we are interested in photon active interrogation, photon-induced fission reactions. Now, here we have to take into account the cross-section values. So to provide some perspective between neutron-induced fission versus photon-induced fission, there is a huge difference in the cross-section. And for different isotopes of interest, like uranium-235, 238, plutonium-239, I have a cross-section plot for reference. And say if we have a 5 MeV neutron, we can get fission reactions in these isotopes. But a 5 MeV photon is not going to give us any fission reaction. So how do we actually make photofission happen? And how do we have a photon active interrogation? So we use our high energy X-rays or Bremsstrahlung radiation to cause photofission. And then in order to compensate for lower cross-section values, we use higher intensity of the photon source. So to give some idea, if we have a DD generator is emitting neutrons at 2 MeV, and this DD generator emits neutrons at about 10 to the 6 or 10 to the 7 neutrons per second, depending on the generator itself. But now if we want to use a photon source to cause photofission in the SNM, then we would use a linear accelerator that's emitting Bremsstrahlung radiation at 9 MeV or 10 MeV. And these accelerators are emitting of the order of 10 to the 14 photons per second. So we see the difference here. 10 to the 14 photons per second to 10 to the 7 or 6 neutrons per second, and then 2 MeV neutron source versus a 9, 10 MeV photon source. So this is how we can still get fission reactions in the SNMs. Now, because it's a fission reaction, naturally signatures emitted are quite similar in nature to those from neutron-induced fission. Now, this photon-induced fission reactions, there is less experimental efforts has been made to measure photofission products, but I feel that this is changing now because a lot of researchers are, coming up with very smart ideas of making photofission a more practical solution, and trying to have in-field photon active interrogation detection system. So this the whole photon active interrogation is a very upcoming emerging research area. And before I move into the next topic, I want to take a pause and see if there are questions from the audience. Okay, so let's continue. So I want to continue a little bit more on the photon active interrogation and talk about some of the challenges that are present when we are trying to do photon active interrogation. Number first is the dose delivery. Now, we have to be careful how much dose is being delivered during the photon active interrogation, because we have to keep this in mind. There will be an operator who will be operating the accelerator and performing the whole active interrogation experiment in fields. And then also if this whole detection system is deployed at ports of entry for possible cargo scanning, then you have to take into account how much dose is being delivered to the cargo. Cargo is very precious. So dose delivery is very, very important. And this presents us challenge because, as I showed earlier, the cross sections are very low and we cannot use low energy photons. So we have to find a sweet spot where we can get enough photofission reactions in the S&M and we don't deliver a lot of dose to the cargo itself and the operator who is performing the active interrogation experiment. The other problem is non-target photoneutrons. Now, when you have photons, with energies like 9 MeV up to 20 MeV, then we start to get nuclear reactions, different kinds of nuclear reactions, along with the photofission reaction. And for up to 20 MeV, you can have a gamma N reaction, gamma 2N reaction. The neutrons that are produced through this photo disintegration reaction are not of interest because this is not giving us any information on the nuclear material because we want to detect prompt neutrons. So what this does is these neutrons start to constitute a background, which I will talk about later in the presentation. And then the other one is the photon flash. Now, normally, for instance, if we are using linear accelerators, these linear accelerators are pulse mode, and I gave you some perspective number, 10 to the 14 photons per second. Now, in presence of this 10 to the 14 photons per second, we want to detect prompt neutron. So our photon signal is so strong during photon active interrogation, and we're trying to detect, in comparison to the photon signal, small amount of prompt neutron and delayed neutron signal during active interrogation. So this poses some challenges during our photon active interrogation. So as I said earlier, we have these two possible reactions that are happening. The up to 20 MeV energy, photon energies. We have photo disintegration reaction and photofission reaction. But there is a way by which we can separate out fission neutrons from the photo disintegration neutrons. Let's consider a simple case where we have a gamma N reaction. Now, gamma N reaction, the neutrons that are produced through this particular reaction will have limited kinetic energy. So this kinetic energy that is carried away by the neutron will be a function of two parameters. One is the Q value of the reaction, gamma N, and the second is the energy of the incoming interrogating photon. So the maximum energy that the neutron can carry away is going to be equal to E gamma minus the binding energy of the gamma N reaction. But in photofission reaction, this is not the case. When fission happens, we know that neutrons are emitted with the Watt energy spectrum. And in Watt energy spectrum, you get neutrons up to 10 MeV in energies or even higher. So we get plenty of high energy neutrons, and we can use this energy information of the neutrons to separate out fission neutrons from photo disintegration neutrons. Any questions on this? Okay, so the final topic that I want to talk about in today's lecture is this whole concept of active background. Then in active interrogation, we have to be, this active background, it plays a very important role. Now, doesn't matter what you use as your interrogating source, neutrons or photons, we always have this active background. Now, where is this active background coming from? So the first is, of course, your interrogation source. The ionizing source that is used to interrogate the target is basically background, because that's not the signal for us. So that's one. The second one is this source radiation can scatter from surrounding materials, and that will cause a signal in your detection system. So that is again background for us. And the other one is secondary interactions. Now, for example, if we have a photon, as we discussed during photon active interrogation, the photon gets absorbed and we have a gamma end reaction, a neutron is emitted. So this neutron is not coming from fission event. So this particular signal is a background signal for us. So this active background is always present, and it interferes during and after interrogation. So we very carefully have to quantify and see what the active background levels are. And this is where the geometry plays a very important role. We don't want to have a lot of high Z materials around our interrogating source or our detection system, or scatter materials around our detection system. If you're trying to deploy the entire system in fields, we have to be smart in how we design our systems, because all this background is going to interfere with our signal terms, and that's going to make the detection of prompt neutrons very tricky. Now, generally, the whole active background, they talk about two types of active background. One is direct active background, which is very obvious, that is coming from the interrogation source particles. And the second one is indirect active background, and this it comes from the secondary particles that are created by reactions between the interrogating radiation and surrounding materials. So yeah, we always want to have a good understanding of what the active background looks like, so that we can correct for it during our active interrogation experiment. And then we know that the neutrons, after correction, if we still see neutrons with high energies up to 10 MeV, then we know that these are coming from fission, and we can raise a red flag and identify the SNM. So I have an exercise that we're gonna do in today's class. So Chris, do you mind creating breakout rooms? So what we're gonna do is we're gonna send you all in breakout rooms, and I want all of you to have a discussion on this particular scenario. So there are two barrels, and these two barrels are actively interrogated by a 10 MeV monoenergetic photon source, and one contains depleted uranium and the other contains lead. We have a detection system that consists of organic scintillation detectors, and they're detecting neutrons produced during the interrogation. So the question is, how are we going to identify which barrel contains depleted uranium and which one contains lead? So the answer is, based on the points that we discussed in today's class. I've also included a cross-section plot for you for your reference. Make sure to use it. And then let's see, I'll give about 10 minutes. And then after 10 minutes, we come back and then we can discuss our findings. So Chris, I'm going to ask you to open breakout rooms now. All right, welcome back, everyone. I hope you guys had a great discussion in your breakout session. So let's see. Any group wants to volunteer and talk about their discussion and findings on this particular situation. Just feel free to unmute yourself and go for it.
Hi everyone. I'm not pretty sure about it, but if you want to talk about it, detectors, and the spectrum coming from this detector, the spectrum, which is I think related to lead, and the other one with lower spectrum is from depleted uranium.
So you mean to say that neutrons with low energies are emitted from depleted uranium, and with high energies are from lead? Is that what you're trying to say?
Yeah.
Okay. Anyone else? Thank you for volunteering. Yeah, anyone else wants to whether agree, disagree? Yes.
I think I disagree. I think so. Depleted uranium should still contain some amounts of fissionable material, and so you would get some high energy neutrons from the depleted uranium, where you get none from lead, which is not fissionable at all.
Correct. Can you identify yourself to the whole group? So
I'm Daniel Jackson from Lannel.
Thank you, Daniel. Yes, that is correct. The depleted uranium, as we look at the cross-section plot, at about 10 MeV, we can get decent amount of fission reactions. So according to physics, if you get fission reaction, then you have neutrons up to 10 MeV, watt spectrum energy neutrons. And you also have photodisintegration reaction in uranium-238, depleted uranium. And the total neutrons that are emitted from uranium-238, majority of those neutrons will come from the photodisintegration reaction, just because the cross-section is higher and it has a low threshold for photon energy. But you will still get some neutrons from the fission event, as Daniel said, and that will give rise to a spectrum, a much harder spectrum. But when we talk about lead, now lead, there are 4 isotopes, 204, 206, 207, and 208. And when we look at the cross-section values, they look quite similar. They pretty much all have a threshold at around 7 MeV, and you do 10 minus 7, so you expect neutrons. The maximum energy neutron from lead is going to be 3 MeV. You're not going to get anything greater than 3 MeV. And this is how we can separate out actinides from other high Z targets in photon active interrogation scenarios. And this is a very, very strong strength of this photon active interrogation, because the energy information is very important. And tomorrow, you guys have a very interesting lecture coming up, which is going to talk about various detectors that are used in active interrogation. And that will, help understand what type of detectors we should use in active interrogation and get this energy spectroscopy information and not just count neutrons produced. So this is all I have got for you today. I'm going to be online for a couple minutes to see if there are any questions from everyone. And yeah, my email address is on the slide. So if you have further questions and want to reach out to me, that's perfectly fine. Just shoot me an email and just let me know that you're from the MTV summer school. So Yeah, thank you, everyone. If there are any questions, please let me know.